So in this video, I'm going to briefly touch on the different situations we've encountered in class that involve exponents. So let's start with this situation. In this expression, I have 3x to the fourth being added to 5x to the fourth. So the operation is addition. This is telling me I need to combine like terms if possible. And since the first term has an x to the fourth, and the second term also has x to the fourth, the variable components of those terms are identical, so they're like terms and they can be combined. If I have 3x to the fourth in this group, and I'm adding 5x to the fourth to that, then altogether I have 8x to the fourth. The variable doesn't change in my answer because my like term needs to stay like. If I'm adding x to the fourths to more x to the fourths, I'm going to have a bigger group of x to the fourths. So it's kind of like saying having 3 apples plus 5 apples is equivalent to 8 apples altogether. If I change this exponent, then it would be saying 3 apples plus 5 apples equals 8 oranges or some other kind of object. And that's not what's happening in this case. So if the operation is addition, we're just combining like terms. Now let's take a look at this situation. This expression is asking me to multiply 3x to the fourth times 5x to the fourth. Now when I think about it, this 3 coefficient and the x to the fourth are side by side multiplying, as is the 5 times the x to the fourth here. So I basically have one huge multiplication problem. So if I wanted to expand this out, this exponent is only immediately directly touching the x. So expanding it out, I would have 3 times x times x times x times x multiplied to 5 times x times x times x times x. And since order doesn't matter when we're multiplying, we can just multiply the coefficient 3 to the coefficient 5, and that'll give us 15. And then I can see that altogether we've multiplied the number x 1, 2, 3, 4, 5, 6, 7, 8 times. Now the shortcut for this, without having to expand it all out and count up how many numbers are being multiplied, is to use what we call the product rule. And the product rule tells me that if I'm multiplying numbers that have the same base, I can add the exponents. So since both of my terms have the same base x, I could have just added the exponents together to get 8. 4 x's in this group times 4 more in this group gives me a total of 8 x's being multiplied all together. Now this situation is a little bit different. When I look at this problem, I have the quantity 3x to the fourth, all to the fourth power. So if I was actually going to expand this out, the 4 on the outside of the parentheses tells me that I have this entire term inside the parentheses 4 times. So expanding that, I would have the monomial that's inside the parentheses written out 4 times. And that monomial is 3x to the fourth. So expanding that, I would get 3 times x times x times x times x times 3 times x times x times x times x. This is just 3x to the fourth, expanded out, times 3 times x times x times x times x times 3 times x times x times x times x. So it's one big multiplication problem again, and I can see that 3 times 3 times 3 times 3 is 81. I could have also written that as 3 to the fourth. That's in using my exponent notation, but actually multiplying it out, since I know the number, I know the base, that I would get 81. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 x's being multiplied all together. Now to avoid having to expand that all out and count up the x's, we could have used what's called the power rule. So the power rule tells me that if I have a monomial as my base. It has to be a monomial. It can't be a binomial. But if I have a monomial as my base, I can kind of like distribute this exponent to every base that's in that monomial. So the number 3 here technically had a 1 exponent, and this exponent 4 is only acting on the x. So I need to distribute this exponent 4 to the base 3, and I need to distribute this exponent 4 to the base x. Oh, hello, y'all can come in. I'm just videotaping, so y'all can go through. It's for my students.
Sorry.
Hello, Mr. Willie.
And we'll be out of the
student.
Okay.
Student. So, sorry. So, distributing this exponent to each base in this monomial, I see that this 3 already had an exponent of 1. So if I try to distribute the exponent 4 to that base, it already had its own exponent. So it's like I have the number 3 4 times, or I could have written it like this. 3x to the fourth, distributing this 4 to the base 3, when it already has an exponent of 1, puts those exponents side by side. So those are going to multiply together in a minute. And the same thing will happen when I distribute the exponent 4 to the base x. That base x already had its own exponent, and now I'm distributing 4 to that, and I'll end up multiplying that. So I'll get 3 to the 4th, which is 81, and x to the 16th, which we got by expanding and counting. So whether you want to expand it out or use your power rule, you end up with the same answer. Now, expanding it out is going to get a little more difficult if this whole monomial was to a negative exponent, and we'll talk about that a little bit later. So knowing this power rule is going to be really helpful when we start dealing with negative exponents. I did want to take a second to point out that if we had a binomial as our base, we could not distribute the exponent to the terms inside this binomial. We would have to expand the base 4 times, and then in this case, do a lot of multiplication, a lot of distribution to get our final product. But if there's a binomial or a trinomial as your base, you're not going to distribute the exponent. It's only allowed if there's a monomial as our base. So looking at some similar problems, let's say we had something like this. 7x to the 3rd plus 4x squared. Okay. Now this expression is asking me to add these two terms together. But when I look at the bases and their exponents, they're not identical. So these are not like terms. So this expression is as simplified as it gets. However, if I was asked to multiply those two terms, then I can follow my product rule here. Because this is one big multiplication problem. If I have 7x cubed, I really have 7 times x times x times x times 4x squared. That's really 4 times x times x. So it's one big multiplication problem here. Multiplying our coefficients together, we get 28. And multiplying our variables together, that's 1, 2, 3, 4, 5, that's x to the 5th. Or we could have used our product rule and added our exponents together. So I just want to point out that addition, combining like terms, has its own set of rules versus a product or power. And the best way to get these rules just ground into your head is to do lots and lots of practice problems.